this lecture, we will explore the local behavior of a non-constant holomorphic function defined on an open connected set omega. We will prove that given a point z0 in omega, there exists a neighborhood u such that in the punctured neighborhood u minus z0, our function f is an M to 1 mapping. We'll come to that, but before that, let's prove a special case of the inverse function theorem, which states that if the derivative of the function f does not vanish at a point z0, then the function is locally invertible in a neighborhood of z0. And further, we have a holomorphic inverse. Let's begin this lecture by proving a preparatory lemma which is needed to prove the inverse function theorem. Let me write that down. Let f be a function holomorphic on an open set omega. Be holomorphic on an open set omega. Then define capital G from omega cross omega into C given by G of z comma w. This is defined to be equal to f of z minus f of w by z minus w when z is not equal to w, and f prime at z when z is equal to w. The lemma states that this function g is a continuous function. Then g is continuous on omega cross omega. The first observation here would be that away from the diagonal points z is equal to w, the continuity is quite straightforward. We only need to really bother about proving continuity at the diagonal points. We shall prove continuity along the diagonal. On the points z is equal to w, which is the diagonal. The first observation in this direction would be the following. Given z0 in omega, let's try to prove that on some neighborhood of z0 comma z0 in omega cross omega, we will be able to talk about continuity of G. And in order to do that, let's first pick a neighborhood. Since f prime is also a holomorphic function and in particular a continuous function, we have R positive, given an epsilon positive, and R such that for z comma w in dz0r, we have, or maybe just some point z in dz0r, we have the absolute value of f prime at z minus the absolute value of absolute value of the derivative of f at z minus the derivative of f at z naught. This is less than epsilon. This is just by using the continuity of f prime at the point z naught. Now, in this disk dz0r, let's pick 2 points. Pick z comma w in dz0r, where z is not equal to w. Now, if you look at the disk, it's a convex set. In particular, if you look at the line joining z and w, that's contained in dz0r. Let gamma of t be equal to 1 minus t times z plus t times w. Be the straight line joining for t in 0, 1. Be the straight line joining z to w, and notice that gamma prime of t is just equal to w minus z, again for t in 0, 1. So, we know exactly what the derivative is as well. It's a nice curve, straight line curve, and we know this. Now, if you try to integrate f prime of gamma of t dt from 0 to 1. Notice that this is a real integral once we break it up into real and imaginary parts. We can multiply and divide by w minus z here, and w minus z being a constant will come out, and w minus z is also the same as gamma prime of t dt from 0 to 1. And if we are to use the change of variable formula now, this is just the integral over gamma f prime of z dz. And now by invoking the fundamental theorem of calculus, this is going to be f of w is the end point minus f of z the initial point by w minus z, which if you notice is g of z comma w. Right? When z is not equal to w, that's precisely how we had defined g of z comma w. Now if we consider g of z comma w minus g of z0 comma z0, this is just equal to the integral 0 to 1 f prime of, recall what we started off with, this is what we had started off with, 0 to 1 f prime of gamma of t dt, and g of z0 is just f prime at z0. But if I write it in this manner, it's the same, and hence if you look at the absolute value here, that's the absolute value here, which is the absolute value of the integral from 0 to 1 of f prime of gamma of t minus f prime at z0 dz, sorry, dt. And we know that being a convex set, for every t, gamma of t is in dz0 r, and therefore f prime of gamma of t minus f prime at z0 has absolute value less than epsilon. So this is less than or equal to epsilon. That's precisely what we were trying to prove, right? So hence in dz0 r cross dz0 r, which is the neighborhood we were looking for, we have, of course, if you are going along the diagonal, there is nothing to prove anyway, and therefore let me just directly write that, maybe none of this is needed, let me just directly conclude that hence G is continuous at z0 comma z0 in omega cross omega. That's what we were trying to prove. Of course, I have not addressed all possible scenarios, but the other ones are quite simple and straightforward. You can sit down and think about it. Now that we have this preparatory lemma, let's jump into the inverse function theorem that I was referring to. The statement will go as follows. The theorem, let f from omega to c be holomorphic on an open connected set. Let me this time use, or maybe not, connectedness is not yet needed. Let's see, I will add connectedness if it is needed later. Open set such that, let suppose z0 is a point in omega such that f prime at z0 is not equal to 0. Then there exists a neighborhood u of z0 such that f restricted to u is injective, or neighborhood u of z0 in omega. So the neighborhood u is contained in omega, and hence we can restrict our function f to u, and f restricted to u is injective. Furthermore, we have f of u is an open set. Let's call it v. V equal to f of u is an open set, and the inverse G from V to U of F is holomorphic. I'll urge you to go through this statement once more. Let me summarize this theorem for you. It basically tells us that if our holomorphic function satisfies the condition that at a point z0 its derivative does not vanish, locally we can get hold of a inverse of this function g, which is also holomorphic. In the process, we do have that a neighborhood of z0 is mapped to a neighborhood to an open set in the image. Let's give a proof of this statement. We will be using the proprietary lemma that was proved earlier, and in order to do that, let's pick some epsilon. Let epsilon be equal to f prime of z0 absolute value by 2. Notice that f prime at z0 is a non-zero complex number, and therefore our epsilon is also going to be non-zero. Now there exists a neighborhood from the previous lemma by the lemma above, or rather the proof of the lemma above. There exists a neighborhood. What is the neighborhood? D z0 r of z0 such that for z comma w in dz0 r, let's call this neighborhood u. This is going to be our candidate for the u. So I'll just start writing u from here. For z comma w in u and z is not equal to w, we have the absolute value of f of z minus f of w by z minus w minus f prime at z0. This is less than epsilon, which is in our case f prime at z0 by 2. Now let's do some manipulation using the triangle inequality. Let me write this inequality in this manner now. This is greater than the absolute value written to the left here, which let me say is greater than or equal to the absolute value of f prime of z0 minus the absolute value of f of z minus f of w by z minus w. So I have used the triangle inequality here already, a version of it, to write this particular step, and we can finally conclude that f of z minus f of w, by bringing it to the left, this is greater than mod of f prime of z0 by 2 times mod of z minus w. What does this tell us? This tells us that if z is not equal to w, in particular f prime of z0 is not equal to 0, so this number is going to be a positive number. We have f of z minus f of w will have a positive absolute value, which implies that f of z is not equal to f of w. So we now have a neighborhood, hence f restricted to u is injective. That's the first statement we had written in the theorem. Let me go up and show you the theorem for you. F restricted to u is injective was the first observation that we had to prove. Let's next try to prove that f of u is an open set. And to do that, let's pick some point, arbitrary point in f of u, and we will prove that that's an interior point of f of u. That is our next goal. So to do that, let's start with some point. Let's start with some a in u. We will show that f of a is an interior point. That will prove that f of u is an open set. Interior point of f of u. Right. So if a is some point, then being an open set, u being an open set, there exists some r is taken. So let s greater than 0 be a positive number such that the disk of radius s around a, the closure, is contained in u. Now let's apply our conclusion here that we had earlier taken to the points on the boundary of the disk of radius S around A and the point A. Notice that the closure being contained in U is going to be used crucially. Then let me put the equation number or maybe a symbol. By star, what do we have? We have f of A plus S e to the power I theta. For all theta we have, theta in R in fact. Well, theta in R or 0 to 2 pi doesn't make a difference. Let me put 0 to 2 pi. Every point on the circle of radius S around A, that's what is meant, minus f of A. Notice that both these points are in U and therefore this is greater than mod f prime of z0 by 2 times mod of z minus w, which is just going to be equal to S here. So let's call this number as C. If you notice, the right hand side depends neither on the theta nor on A. It's some constant number S. This is good. So what is being said is that what is being concluded here is that f of A plus S e to the power I theta is always outside a disk of radius C around f of A. So if you have f of A here and suppose this is the disk of radius S, radius C around f of A, then f of A plus S e to the power I theta will be outside this disk of radius C. So in particular, let us pick some point W in D f of A C by 2. Let's take a disk of radius C by 2. Then any point inside this disk will be at a distance greater than C by 2 from any of the f of A plus S e to the power I theta, isn't it? Then it's just a triangle inequality thing that I have written here, which I am writing here, f of W minus f of A plus S e to the power I theta. This is going to be greater than C by 2. So even though I just said that this is the case by looking at the picture, it can be established by writing down the triangle inequality in the right manner. So this is something which we can conclude for all theta in R or in 0 to 2 pi. Now suppose our function f does not take does not have W in its image. Suppose there does not exist Z in U, not in omega. Let's focus just on U. After all, we are studying something local here. Suppose there does not exist a function Z in U such that f of Z is equal to W. Suppose we do not have such a function. Maybe I should put a W naught here. W sounds more generic, so let me put a W naught here. Suppose we don't have any point Z getting mapped to W. Then consider G of, if you look at f of Z minus W naught, this function, then this function does not vanish on U. It does not vanish on U. And hence, G of Z equal to 1 by f of Z minus W naught is holomorphic on U. Now let's invoke the maximum principle. We are in a perfect setup to apply the maximum principle to this holomorphic function G. And what compact set? The compact set that we are going to use is D0, DZ0 R bar, sorry, S bar. We will use this particular compact set and use the maximum principle. What can we conclude by the maximum principle? Maximum principle applied to G and compact set DZ0 S bar. Remember that G is a function which is holomorphic on U and dz0s bar is a compact set contained in U. The maximum principle, absolute value of g of z is less than or equal to the supremum over the boundary, which I will now write it as supremum over theta, absolute value of g of oh, I'm sorry, this is not what I want exactly, it's A. I made a mistake, this is not z0, this is A. Yeah, everything else is right, and the supremum will be over the boundary s e to the power I theta. That's precisely what our maximum principle will tell us for all z in DAS. But then what do we have? Supremum of g, this is nothing but 1 by f of a plus s e to the power I theta minus w, the absolute value of this. And we are looking at the supremum of this quotient, which is going to be 1 by infimum over all theta, which satisfies this. So let me write that down. This is going to be 1 by f of z minus w. This absolute value is less than or equal to this infimum, which tells us that the infimum over theta, absolute value of f of a plus, I picked a w naught, right? So let me put w naught. Right. This absolute value is infimum over this absolute value is less than or equal to the absolute value of f of z minus w naught. But notice that to the left, we know that for all theta, absolute value of f of a plus s e to the power I theta minus w naught is greater than c by 2. If you notice, that's precisely what we had concluded here. Where did we conclude that? The line I am underlining in green exactly said that f of w naught is at a distance of at least c by 2 from any point on the boundary f of s a plus s e to the power I theta, and this tells us that the infimum will also be greater than or equal to c by 2. And what about the right hand side? We know that f of z minus w naught, this is strictly less than c by 2, because w naught, okay, in particular f of a minus w naught is also less than c by 2, right? This is true for all z. Let me just note that this is true for all z in DAS. In particular, it's true at the point A as well, and therefore this inequality should hold at the point A as well. But that is a contradiction, because this left hand side is greater than or equal to c by 2, and the right hand side is less than c by 2, and therefore this inequality is not going to hold. There is a contradiction, which is a contradiction. So our assumption has to be false. What was our assumption? This was our assumption. If we are assuming that W0 does not have a pre-image in U, then by applying maximum principle, we have come to a contradiction. And therefore, hence, there exists some Z in U such that f of z is equal to W naught. But that's precisely what we were trying to prove, right? This tells us that d f of a c by 2, this particular disk in the complex plane is contained in f of u, right? Notice that our W naught was picked here. So in particular, we will be able to conclude that this particular disk is contained in f of u, and hence f of a is an interior point. So we are good, because now what have we established? We have established that f of u is open. So let's call it v equal to f of u is an open set. So that means f restricted to u is a bijective map from u to v. We already started off this proof by establishing that on u f is injective. We have also shown that it maps onto u and onto v, an open set. Therefore, this is a bijective map. Now let G from v to u be its inverse. We will show that G is a holomorphic function on v. So to do that, let w naught, maybe w naught was okay, w prime be a point in v. Let's try to prove that G is holomorphic on w prime. To do that, let's look at for w in v and w not equal to w prime. Let's look at what is g of w minus g of w prime by w minus w prime. Now the good thing here is that v is exactly f of u, and because of that we will be able to get hold of z in u and z prime in z and z prime in u, such that f of z is equal to w and f of z prime is equal to w prime. Notice that f being injective ensures that z and z prime are distinct. So writing this, we will be able to get the following here: g of f of z, g is an inverse, so this is going to be z minus z prime by f of z minus f of z prime, and we can write this as 1 by f of z and f of z prime are distinct. That's what the point here is, and hence z minus z prime is also distinct. So we'll be able to write this as f of z minus f of z prime by z minus z prime. We are almost through, because now we just have to show that as w goes to w prime, z goes to z prime. So the claim is the following: as if limit, if we take a sequence w converging to w prime, then z converges to z prime, where f of z is equal to w. And the observation follows again from star that was noted earlier. Let me just go back to that inequality. So this is the inequality in question. This tells us that the absolute value of f of z minus f of w is bounded below. Let me write that down here. We have absolute value of f of z minus f of z prime. Let's now focus on u. This is greater than absolute value of z prime, f prime at z0 by 2 times z minus z prime. But then what is this inequality? F of z can be written as w, and this is w prime. So let me just write it the other way: absolute value of z minus z prime. This is less than some constant times, constant is 2 by absolute value of f prime at z0, and this is f of z will just be equal to w, and f of z prime is just equal to w prime. So in particular, if w is converging to w prime, z will also converge to z prime, and hence we have this claim, and thus we get to conclude that limit as w going to w prime of g of w minus g of w prime by w minus w prime, this is equal to the limit as z goes to z prime, where w is in u minus w prime. We have used the injectivity of f very crucially. So this is going to be the limit as z is in, okay, this is in v minus w prime, this is going to be in u minus z prime of 1 by f of z minus f of z prime by z minus z prime, which is equal to 1 by f prime at z prime. Okay, the two primes shouldn't be confused. One is f prime and the other is z prime. So in particular, our function g is complex differentiable at every point in our given domain omega. And I'll leave the conclusion to you to conclude that hence G is holomorphic on V. That's what we were trying to prove. So let's just recap what we have established. We proved that if we start off with a holomorphic function whose derivative does not vanish at a given point z0, then we get a holomorphic inverse. This is also sometimes called as f being a local biholomorphism. Biholomorphism is a holomorphic map whose inverse is also holomorphic. So this is a local biholomorphism. All right, let's now look at one particular function very specifically. Let's consider this function z going to z to the power m. Let's call a name to it, pi m from C to C. The map pi m of z equal to z to the power m. We have seen that this is an entire function and that at any point away from 0, the derivative does not vanishes. For z0 not equal to 0, pi m prime at z0 is not equal to 0, and therefore this function is a local biholomorphism. It has a local inverse which is also holomorphic around z0 when z0 is not equal to 0. So in particular, if we work on some neighborhood, if V is a neighborhood such that V is an open set, neighborhood of what? V is an open set which does not contain the origin. Then at every point we will be able to get hold of a neighborhood of the point z0 whose image is also an open set. That means that pi m of V is also an open set. So you take any open set V which does not contain the origin, then pi m of V is also an open set by the inverse function theorem, but because at every point the derivative does not vanish. How about at the point 0? Recall that by a theorem we have proved earlier, we know the exact roots to the equation z to the power m equal to w when w is a non-zero number. Let me recall that for you. Recall that this was one of the problems we did in a problem session in one of the first few weeks of this course. Recall that if w is equal to r e to the power I theta is not the complex number 0, then there exists then z to the power m equal to w has roots given by zm equal to r to the power 1 by m, maybe zk equal to r to the power 1 by m e to the power I theta by m plus 2 pi k by m, where k is from 0, 1 up to k minus 1. And using this, we can conclude that pi m maps a disk of radius r around the origin to the disk of radius r to the power m. This is exactly what we will be getting. So pi m behaves in a very nice manner, and that's something which we will be going to use to explore how our function, holomorphic function f, behaves locally in a neighborhood of our given point z naught. Let's now explore the local behavior of a holomorphic function in a neighborhood of a point z0 in its domain of definition. We will in fact show that given a point z0, we will be able to get hold of a neighborhood such that on this neighborhood, the punctured neighborhood rather, our function f is an m to 1 function. Given any point on the image, there are m pre-images to it. So let me write down the statement, local behavior of holomorphic functions. Let me write it down as a theorem. Let f from omega to c be a holomorphic function. Maybe more careful. Let me be a little more careful here. It's not any holomorphic function. It's going to be a non-constant holomorphic function. And I want it to be on each component. So let me impose the condition that omega is an open connected set as well. On an open connected set omega contained in C. Let's fix a point. Let z0 be some point in omega and w naught be the image of z naught under f. So w naught is f of z naught. The conclusion is that then there exists a neighborhood u of z naught and bijective holomorphic function phi on u such that f of z is equal to w naught plus phi of z to the power m for z in u and some integer m greater than 0. Moreover, we can arrange for our phi to map u onto a disk. Phi maps u onto D0R for some R positive. Let's look at the statement once more. What this tells us is that if you carefully look at what we have concluded here, we have successfully written down in a neighborhood of z0 how our function f behaves. It behaves in this manner. F of z is w0 plus phi of z to the power m. Phi is an injective map and phi of z to the power m is just pi m composed with phi, and therefore the injective map will be an m to 1 map. So we will come to all the details one by one. The key thing to note is that locally in a neighborhood of z0, we have been able to explicitly find out how our f behaves. Okay, let's try to prove this statement. Since we know that f of z0 is equal to w0, we know that f of z minus w0, this holomorphic function, has a 0 at z0. Since f of z0 is equal to w0, we know that g of z equal to f of z minus w0 vanishes at z0. Let me not unnecessarily bring in notations. F of z minus w0 vanishes at z0. Now, by applying the factorization theorem repeatedly, in fact, I'll use the G now. By using the factorization theorem repeatedly, we can write f of z minus w naught to be equal to z minus z naught to the power m times g of z for some m positive and such that g of z naught is not equal to 0. So a key thing to keep in mind is that while we did this, we have very crucially used the fact that f is a non-constant function, and because of that, all derivatives of f at the point z0 cannot vanish. Because if that happens, then by the principle of analytic continuation, f would be identically equal to 0. And that is precisely the reason why we are able to get hold of one such m to write our f of z minus w0 as z minus z0 to the power m times g of z, and where g of z0 is not equal to 0. Now, since g of z0 is not equal to 0, by continuity, we will be able to get hold of a small disk around z0 where g does not vanish. So, let epsilon positive be, epsilon is not a good and r is already taken. So, s positive be such that g of z is not equal to 0 on dz0s. Let me invoke one of the problems we have proved earlier. You should go back to the problem sessions that we have done earlier. We have proved that if we are in a simply connected domain U, and if g is a function which does not vanish on U, then we will be able to get hold of a holomorphic function h such that g is equal to e to the power h. That's something which we had done while we proved the Cauchy's theorem some time back. I'll urge you to go back and have a look at that problem. Recall that dz0s is a disk of radius s. In particular, it's convex. It's in fact simply connected. So maybe I should write that, since dz0s is simply connected, and g does not vanish on dz0s, there x is a holomorphic function h on dz0s such that g is equal to e to the power, g of z is equal to e to the power h of z on dz0s. Now let's define what our phi is going to be. We have developed every machinery needed to define what our phi should be. Define phi on dz0s to be phi of z is equal to z minus z0 into e to the power h of z by m. So notice what we have done. We have f of z minus w naught is equal to z minus z0 to the power m times g of z, right? So if you look at what is phi of z to the power m, this is equal to z minus z0 to the power m times e to the power h of z, which is equal to z minus z0 to the power m times g of z, which is equal to f of z minus w naught. So on dz0s, we already have f of z is equal to w naught plus phi of z to the power m. That was one of the conclusions, right, that we were drawing in this particular theorem. You notice here, of course, we have some more work to do. There exists a bijective holomorphic function phi on u such that this happens. So we have already established that phi is indeed satisfying this condition. We will now prove that it is indeed bijective and holomorphic. Holomorphicity also follows by the very definition. The first thing to notice here is that what is phi prime at z0? If you look at phi prime at z0, that's just going to be equal to e to the power h of z0 by m, which is not equal to 0. And this is precisely where our inverse function theorem that we proved earlier is going to come into the picture. We will now prove that going down to a further neighborhood, let u prime, it's still not the u we want, let u prime be a neighborhood of z0 in dz0s such that phi restricted to u prime is injective and phi of u prime is an open set. By our inverse function theorem, we have this. We should also note that Z0 is, where is Z0 getting mapped? By phi. Our definition of phi is such that Z0 is mapped to 0. So, in particular, since phi of Z0 is equal to 0, we can now use the fact that phi of u prime is open. There exists some, well, I am running short of notations, s prime greater than 0 such that d0 s prime is contained in phi of u prime. Now, define our u to be equal to phi inverse of d0 s prime in u, contained in u. This is the open set we are going to work with. Let's check everything that we need to check. On u, we have f of z minus w naught is equal to phi of z to the power m, and that's what we were trying to prove, right? This is in fact true on the entire dz0s, but rather we can restrict our attention to a smaller set u, where for sure we can say that phi is injective. Phi is bijective and holomorphic on u, and phi of u is equal to, oh, this is not s prime. Why did I pick s prime here? Our final goal was to get hold of an r. So let me use the r as well in this particular place. This is equal to d0r, and that's precisely what we were trying to show. So notice that we were able to write f of z as being equal to z0 plus phi of z to the power m, which is the same as pi m composed with phi of z of z. And the good thing about pi m is that pi m in the punctured disk is an m to 1 mapping, and phi is an injective mapping, and therefore f of z minus z naught, this in fact f of z, oh, I'm writing it wrong, this is w naught, f of z is hence an m to 1 mapping on u minus z naught. Z naught has to be removed because z naught is what is getting mapped to 0 by phi, and therefore on the punctured disk our mapping is going to be an m to 1 mapping. Yeah, this is following because phi of u is precisely d0r. That is why this particular arrangement was made, so that the image is exactly d0r, and then on d0r our map pi m, or rather on the punctured disk d0r minus 0, our map pi m is an m to 1 mapping. So f is going to be an m to 1 mapping on u minus z naught. Let me conclude this lecture by stating the open mapping theorem. Open mapping theorem states that if f is a function which is non-constant and holomorphic on an open connected set omega, then f of omega is open. We will be able to now derive our open mapping theorem as a trivial corollary to the work we have done in this particular lecture. So the open mapping theorem says this: let f from omega to c be a non-constant holomorphic function f on omega, on an open connected set omega. Then f of omega is an open set. The proof is quite straightforward. Let z0 be in omega and w be equal to f of z0, w not be equal to f of z0. By the previous theorem, there exists a neighborhood U of Z0 such that f of z is equal to W0 plus phi of z to the power m on u, and such that phi of u is equal to d0r. If you think about what this means that f of u is going to be equal to, so pi m composed with phi, hence pi m composed with phi of u is just going to be equal to pi m composed with d0r, which is going to be d0r to the power m, and hence f of u is just going to be equal to dw0 r to the power m, which I will just write it as capital R. So hence every point W0 is an interior point of the image. W0 is an interior point of f of omega, and this tells us that f of omega is open. So the open mapping theorem comes out as a simple corollary to the study of the local behavior of our holomorphic function f in a neighborhood of a point z0.